Hey, geometry. So the second part of our first section of probability. So we're going to get into theoretical probability, and then eventually we'll add on some experimental probability. So a couple of different things. So theoretical probability. So probability is a measure of the chance, another way of saying kind of probability, that a specific event will occur. When all outcomes are equally likely, the theoretical probability of event E is the ratio of the number of favorable outcomes to the total number of outcomes. So probability of event E, this is a new notation. So P of E is kind of a probability of event E. We count up the number of favorable outcomes out of the total number of possible outcomes. As long as, then again, this is important that this is if we're dealing with equally likely outcomes. So probabilities have values between 0 and 1 and can be expressed as a fraction, a decimal, or a percent. So some examples. The spinner below is spun once. Find each probability as a fraction in the simplest form, a decimal, and a percent. So this is the one I was talking about in the last video. Now that we're talking probability, we need these actually to be equally likely, and this needs to be a fair spinner that isn't more likely. It's not going to get stuck on 5 over and over again or something like that. So theoretically, if we were going to do this, a multiple of 3. So that would be 3, 6, 9, 12, and 15. So that was 1, 2, 3, 4, 5 out of 16. And so that was the probability we would get that 5 favorable outcomes out of 16 possible outcomes. So that would be the fraction in simplest form. We can't reduce that. A decimal, if we do 5 divided by 16 in our calculator. So 5 over 16, we get 0.3125, which is equal to 31.25%. Just move that decimal a couple places, times 100 per 100. So 31.25%. A prime number. All right, so this one's a bit tricky. Some people don't realize that, 2 is the first prime number. Let me, hold on a second. So yeah, here we have 2, 3, 5, 7, 11, and 13. So that's 6 prime numbers out of 16. So of course we're supposed to reduce that fraction. So 6 out of 16 is the same thing as 3/8, which is equal to, and we can type that in as a decimal, 3/8 is 0.375. And converting that to a percent, that would be 37.5%. All right, even or greater than 5. So we just want to, there's some other tricky ways we can deal with this, but let's just kind of think about our numbers that are even or greater than 5. So I've got 2, so that's 1, 4, 6, and then basically I count everything else the rest of the way because this is greater than 5. So 7, 8, 9, 10. Let's see, hold on. Let me do this a little bit differently. So we got 6 through 16, which is actually 11 numbers. So even though the difference between those is 10, that is 11 numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 numbers there, plus my other even ones, so 12 and 13. So that gives us 13 favorable outcomes out of 16. That fraction will not reduce, so we can go ahead and type that into the calculator. That is the same thing as 0.8125 or 81.25%. And then last one, odd and at most 9. So and needs to meet both criteria. So odd up to 9. So we've got 1, 3, 5, 7, and 9. At most 9 includes that. So 1, 2, 3, 4, 5. 5 out of 16 works out to be the exact same probability as the first one, 0.3125 and 31.25%. All right, give the answer to the following questions as fractions in simplest form. A pencil box contains 5 red, 12 blue, 10 green, and 3 yellow markers. If a marker is chosen at random, what is the probability that it is not yellow? So the number of favorable outcomes are all the rest, 10 plus 12 plus 5. So that would be 27 favorable outcomes, the not yellow ones. divided by the number of possible outcomes, in this case, 30. All right, and so then reducing that fraction, we can divide both top and bottom here by 3, and so we get 9/10. And that is the fraction in simplest form. We have a 9/10 chance of not getting a yellow. What is the probability of drawing an ace or a diamond from a standard deck of playing cards? So, of course, you need to know a standard deck of playing cards. There are 4 aces, and there are 13 diamonds, but the trick is don't double count. We'll come back to a rule with this. There is also an ace of diamonds. So I've got the 4 plus the 13, but I don't want to double count, so I'm going to take 1 off of that. So it's really, you can think of it as the 13 plus 3 more non-diamond aces, which gives us 16 favorable outcomes out of a deck of 52 cards. So if you need to study up on your deck of cards, Google that. So 16 out of 52, that fraction will reduce. We can divide both those by 4, and we can get 4/13 for that probability. Finn guessed on the last 3 true or false questions on his math quiz. What is the probability that he got exactly 2 questions correct? All right, so this one is actually pretty tricky. So let's think about the possible outcomes. I'm going to draw a little tree diagram out here. So the first one he could get correct or incorrect. The next one he could get correct or incorrect. So I'm going to draw this. And the third one he could get correct or incorrect, correct or incorrect, correct or incorrect, correct or incorrect. And so we're looking for this one where he gets, what is the probability he got exactly 2 questions correct? So that would be correct, correct, incorrect. This outcome would be exactly 2. The first one was all 3, right? This outcome, correct, incorrect, correct, would work. And this one right here, we misses the first, incorrect, correct, correct. So there are 3 favorable outcomes out of, and then so we could count up the possibilities, 1, 2, 3, 4, 5, 6, 7, 8, or we could have just done 2 times 2 times 2, that multiplication rule to say, oh, out of the 8 possibilities. So 3/8, and yeah, that actually is the reduced fraction. Don't need to go any further there. All right, and then 2 standard dice are rolled. What is the probability that the sum of the two dots on the dice is at most 5? Sorry, that should be phrased differently. That the dots on the 2 faces is at most 5. So again, we could list a sample space or draw a tree diagram of all the possibilities. That one gets kind of big because this one had 8 possibilities. If you roll 2 dice, there are 6 times 6. There are 36 possibilities. I just want to know how many different ways can it add up to be at most 5. And so I'm just going to list out some of the ways. So I'm going to just kind of do a partial sample space here of the favorable outcomes. So I could get a 1 and a 1. We could get a 1 and a 2, a 1 and a 3, a 1 and a 4. And that adds up to 5. Can't continue with that line. And I'm going to think about, all right, I could have my first die could be a 2. So I could get a 2 and a 1, a 2 and a 2, a 2 and a 3. And that's it. That adds up to 5. And then you'll kind of see a little bit of pattern to this. I could get a 3 and a 1, a 3 and a 2, but now I'm up to 5. And I could get a 4 and a 1. So, and I can't get a 5 on a die because I can't get a 0 on the other die. So those are actually all the possibilities. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 possibilities. 10 out of 36. We can reduce that 1. We can at least cut those in half. And that's going to cut into 5 out of 18. And that would be our reduced fraction for that one. All right, another example here. Students in a homeroom were asked if they have a part-time job and if they have their driver's license. The results are shown in the Venn diagram. So this is another useful tool we'll have. A Venn diagram to the left. If a student from the homeroom is chosen at random, find each probability. Give each answer as a fraction in simplest form. So the probability that the individual has a part-time job. So I want to find the number of favorable outcomes out of the number of possible outcomes. So having a part-time job is everybody in that big circle. And so in that case, it is 8 plus 6, so it's 14. And then I need to figure out how many total people there are. They didn't tell me in the problem. So I had those 14, so plus 4 more, or so I guess plus 7, so I guess 21 plus those 4 more. It gets me up to 25, so 14 out of 25, and that one won't reduce. So we have a 14 out of 25 chance because these students have a part-time job. Remember these 6 in the overlap of a Venn diagram of how long it's been since you've seen one of these. They're in both. They both have a driver's license and a part-time job. No driver's license. So no driver's license not inside that circle includes this 8 and that 4. So that ends up being 12 out of 25. A part-time job and a driver's license. Well, that is that overlap. So that is those 6 out of 25. That's just that cross-section. A part-time job or a driver's license. So that's anybody that has either a part-time job or a driver's license. So or is a more kind of inclusive thing. It can be in either category. So all 3 of those numbers. So it's basically everybody but those 4. So I can either add those 3 numbers or realize it's 25 minus those 4. So it ends up being 21 out of 25. And then the last one, a driver's license and no part-time jobs. They need to have a driver's license and not have a part-time job. So not those 6, just these 7 over here, 7 out of 25. All right, next one. Out of 60 students, 15 are taking calculus and 27 are taking physics. 8 of the students are taking both calculus and physics. If a student's group is chosen at random, find each probability. So actually, let's draw a Venn diagram to help us with this. This is another tool that can be useful. So I've got 60 total students. We've got our calculus students and our physics students. I'll just call them C and P. So I know 15 are taking calculus, but careful, that's the entire circle. So I'm actually going to start, when you're doing a Venn diagram, it's good to start with the overlap. 8 of the students are taking both calculus and physics. So I've got 8 here. So then out of those 15 that are taking calculus, if that's 8 of them, that means the other 7 are just taking calculus and not physics. So that ultimately gives us 15 students in calculus. And if there are 27, that means this must be 19 over here that are just taking physics. And so then last number I can figure out here is how many left over are there that aren't taking either of those, right? That are out here in the rest. And this box out here represents our sample space, all of our possible outcomes for students. So that's 60. So we had... I could add, I had these 15 plus those 19 more. And so that's going to leave us with, so let's see, 15, 19, that's 34. So that leaves us with 26 out here. So the student takes calculus or physics. That's all 3 of those numbers together. So that again is those 34 out of 60. Looks like we can reduce that. We can split each of those at least in half. So that's 17 over 30. Which is fully reduced, and then takes calculus but not physics. So that is these 7. They're in the calculus bubble but not in the physics bubble. So 7 out of 60, and that can't reduce. We kind of already dealt with this a little bit, but the complement of an event is the probability of the event not occurring. And so we already had some of those that something does not happen. We kind of looked at the opposite, everything else. Since the sum of all the probabilities in a sample space is 1, so the probabilities of all the possible outcomes has to add up to 1. The probability of an event not occurring is, so this is how we write this, the probability of not E. We use this little squiggle, tilde, E. So the probability of not E is 1 minus the probability of E. And so we can figure those out pretty quickly. The probability that it will rain tomorrow is 11 out of 15. What's the probability that it will not rain? So we can just do 1 minus 11 out of 15, which, if you need a little reminder, we could think of that as 15 out of 15. Minus 11 out of 15 leaves us 4 out of 15 would be that probability. A number from 1 to 30 is selected at random. What is the probability of not selecting a multiple of 4? So I could think about all the numbers that are not multiples of 4, like 1 and 2 and 3 and so on. Or it might be easier just to work this out the other way, figure out how many multiples of 4. So the probability that I get a multiple of 4. And so that would be 4, 8, 12, 16, 20, 24, and 28. So there are 7 possibilities. So 7 out of the 30. So that's the probability of getting a multiple of 4. So the probability of not getting that would be 1 minus 7 out of 30, which leaves us the other 23 out of 30 ends up being our answer to that one. And this is the probability that we not multiple of 4. It's not multiple. So it's going to be 1 minus 7 out of 30. We got a messy. 23 out of 30. All right, and then the last bit, this is I mentioned, so we can do theoretical probability by just counting up equally likely events. Experimental probability is based on the results of repeated trials of an experiment. For example, the spinner to the right is spun 50 times. The results of each spin are shown in the table. And so, you know what? This spinner looks fair, right? It looks even. Looks like it should be about 1/5 all of them. But in reality, sometimes, it may not be that way. In fact, we see there were a lot of oranges and yellows. Maybe the spinner gets a little stuck on yellow and so on, and not so much on red. It's nice and smooth through red, so it's not really a fair spinner. And those of you that have played games, you know that can happen with spinners. They don't seem to always end in the same spot if they're not really perfectly mechanically designed. Oh, so find the theoretical and experimental probability if the spinner is spun again. So theoretically, the probability of orange appears to be 1/5. But experimentally, as we can see, as we've observed over time, the probability of orange is 12 out of, and so then we need to add up all those spins. Actually, they told us there that spun 50 times, so that's nice. 12 out of 50, which could reduce to, what can we divide that by? So I guess that would be the 6 out of 25, which is, not the exact same. 1/5 would be 20%, 6 out of 25, what would that be? 6 out of 25, I guess I should have been able to do that. That's 24%. So seems like, and experimentally we observed it's a little more likely, right, and we saw that in orange, than we would have expected theoretically. The probability of red or green, all right, so that would be 1/5, like 2 out of 5. It looks like it'd be 2/5. Well, red or green, if we add those up, we get 15 out of 50, and so that would be the same thing as 3 out of 10. So we're expecting 40%, but we got 30%. So those seem to be a little bit less. And then the probability of not purple. So purple, we see there's 1 out of 5. So we'd expect it to be 1 minus that, which would be 4 out of 5. But not purple. We could add up all these other ones, or we could find the probability of purple, 7 out of 50, and do 1 minus that, and get 43 out of 50. And yeah, those don't end up being the same. This ends up being about 80%. That's like 86%. So, and sometimes the decimals are nicer to compare than the fractions, but I'll stick with the fractions on that one. And so there is some experimental probability as well. So probability is that long-term chance, the long-term kind of how often it occurs, what we expect, if it's theoretically fair, but a lot of times, sometimes what is observed is that it's not, it's not exactly that, your die may or may not be fair. And for things like I said, you can think about the probability that your phone cracks when you drop it. We can't calculate that theoretically, or at least it would be extremely hard to. So we can do that experimentally, though. You just have to drop a bunch of phones and see how frequently it breaks, which, there might be actually testers that do stuff like that. So that is theoretical and experimental probability.